Well, good morning, everybody. It's good to see you all again. We're going to pick up where we last left off with operational space control coding. Okay? You can start off directly where my code is by going to the Canvas page. It is now uploaded. Thank you for your patience while we got that up there. You can go and download particularly the ARM dynamics and the anyway, you can download the 5 files on there. In fact, you know what? You can see right now. You can see right now where we left off. Okay, here we go. We got this. Okay, so we've got a couple. We have 5 functions or 5 scripts, 5 files, M files in our coding last time, and you can get our most recent version on Canvas. And the way we handled it was we had a gen arm functions script. And the sole job of this script was to generate functions that other scripts will need, okay, or other functions will need. So and this is going to generate, for instance, our dynamics. Now we were going to try to debug these dynamics, okay, and we're still going to try to debug these dynamics. We're going to debug it together today. I didn't go and do it offline, partly for the learning experience here, okay. See what's going on, see if everything makes sense. Okay, that's one. Okay, number 2, we also have this simulate arm script, and its job is just to simulate the 2 degree of freedom arm. That's what we were doing. And just as a little reminder here, we had this little 2 degree of freedom arm set up here where we have a torque on both of those joints, and we're going to try to make this track a position. You know, we're going to have it make it move around and apply torques to track around. That's what we're doing. Just to remind everyone, that's what we did on Thursday. So I have these initial conditions. All right. And if I run my simulate arm script, I should get a little animation pops up. Okay, anytime now. Busy. All right. And it's like, and I was looking at this little shaking of this pendulum, but it wasn't quite right. It's like, let's see, is that right? Is that right? Well, let's try a few initial conditions. This actually sort of mirrors what you should do anytime that you are simulating a new project, you come up with new equations. Does this make sense? Now, it's not swinging upward. That's a good thing, right? That's a good thing. So let's try a couple of other initial conditions. Let's try an initial condition of 0, and this should be the arm out to the right, and then the other arm out to the right as well. And let's just give it a 0 initial velocity, 0, 0, 0, 0. Let's see what happens. Does it make any sense? You should have a double pendulum here. Oh, that's bad. That's real bad. That's not good. That's gaining energy right there. You can tell because it's swinging around so fast. Something's up. Something ain't quite right. So where could things go wrong? The average pendulum experience. There we go. Agreed, Logan. All right. So let's code here. Fine. So we got our plotting of our angle. Okay, it's not going to be in our simulate command. I think we're simulating everything probably pretty well. All right. But we are calling the arm dynamics function. The arm dynamics function is also quite simple. So we can see if there's something going on here or if there isn't with fresh eyes. All right. Again, I haven't looked at this since Thursday, so maybe fresh eyes will help. All right. So these are our dynamics functions for our ODE solver. I'm going to send back the derivatives of our 4 states, and we try to calculate the accelerations by taking this inertial matrix, taking the inverse, and then multiplying it by our bias terms, right? And looking at this, there's not much room for us to screw up. Yeah. So this is our first state, second state. Yeah. So that seems right. This seems right. I mean, our M funcs are this is our inertial matrix here. Okay, this is our bias. Our inertial matrix is only dependent upon Q, which are our positions. Okay, and our bias is dependent upon Q and DQ, so our positions and velocities. At some point, our torques as well. We'll get to that. We'll get to that, all right? Hopefully soon we'll get to that. I want to actually make this all work here. The derivative of each of the states, that looks right. So I don't think it's the arm dynamics. So it's going to take us into the granddaddy of where things could be going wrong in our generate arm functions. Where could we be screwing up? Now, one thing we could do is we could try to isolate certain elements of the dynamics by changing our parameters here, okay, and turning certain things to 0. For instance, one thing that is new in this version of our code for this problem is we added rotational inertia. And you can see that rotational inertia right here. This is your 1/2 I omega squared. Okay? And actually, I'm looking at this right now. 0, 1, 0, 2. I do want to make, maybe, I think that this is right, what we did here. Okay, we'll take a look. But one thing we could do is we could just turn off our rotational inertia. We can make the rotational inertia 0, and then this term here won't exist, right? So we could see that, hey, if we just have masses halfway down our pendulum, if you call it, looks like this. Here's our pendulum, right? Is there a better drawing I have? Is a little bigger? Let's see. Here we go, a little better. We only have these masses and no inertia, rotational inertia. Yeah, and Logan, that's a great question. That's a great question. Let's get to that. Maybe so Logan's question is why we're calculating the inertial matrix and not the Coriolis and the gravitational terms. The answer is we are. We're just lumping them all together. That's what we're doing. Okay. So yeah. All right. So let's change the inertia. One thing that's different is that term. So let's see what happens if I change my inertias and my parameters here, to I1 and I2. And I rerun this generate function script. And what's going to do, it's going to generate new bias function and a new inertial matrix. Okay? It's going to generate those functions over there on the left. They're going to be new. And now when we run our simulate arm script, it should have, whenever it's going to be calling our arm dynamics, the arm dynamics is now going to be calling a new inertial matrix, the bias function. Okay? So it should all be updated. So let's run this. Run the simulate arm function, see what happens. Yeah, still things are going wrong. So it's not the inertial, it's not the rotation inertia. We'll keep that term in there. Let's just see what's going on though. What's happening? Okay. I'm just scrolling through, I'm just seeing if there's anything kind of out of place that I would expect. You know, we have patterns of saying DDQ, DDQ, DQ, DQ. Is there something where I copied and pasted wrong? That could be a thing. All right. And not seeing it just yet. Here we have our Euler-Lagrange equations. We have our right-hand side. Minus subs. It could be this term. My guess is it might be something here. So this actually would beautifully take us into the question that Logan has. He says, I'm curious why we only calculated the inertial matrix and not our Coriolis and other matrix. Well, let's to get this all together, let's go back to the board and continue where we left off. All right. So back to the board. So here we are at the bottom. Here we just did our animation. So this is part 2. 2025, 0422. This is part 2. This would be good debugging practice, right? Something we don't, frankly, not to toot my own horn, I did too good of a job coding all this stuff live in front of you. We haven't hit a lot of issues, right? So I'm not giving you the debugging experience. You know, I got to give that to you better here. So I think I'm a victim of my own experience here in coding these things live in front of you. But finally, we hit a tough issue. Let's see what's going wrong. Because clearly the dynamics ain't right. So here's our manipulator form. Of the Euler-Lagrange equations. Okay. Manipulator form. So it has this M of Q, that's our inertial matrix, times Q double dot. Now, we are all adults here. We know Q and Q double dot are time dependent. I'm just not writing it to save us some time. Plus C of Q, Q dot, times Q dot, plus G of Q is equal to some external torque tau, right? And in our code, we said, hey, all this stuff here, all that, let me show how do I draw this here? All this stuff, oh my goodness. All of this stuff here, we called that ELLHS, right? Left-hand side. And all this stuff over here is going to be our Euler-Lagrange right-hand side. Okay? We have this Euler-Lagrange right-hand side. All right? So, excuse me a second. I'm seeing a good question from Roy. A very good question. Okay, no, that's not the answer. So, all right. Okay, I'm seeing some questions roll in. Let me make sure I can see you all your questions here. Could you show your bias function? Because last class we had the biases EL-LHS plus EL-RHS. That's a great question. So here's what we're going to do. Let's go with one step at a time. So bear with me for a second. So I think this all makes sense. If it doesn't, stop me. Okay. So the way that we solve, because the thing we want to solve for here is we want to know where our accelerations are, right? That's that Q double dot. So how do we solve for that? It would be, we would keep on the left-hand side M of Q. I see your question as well, Roy, because I do, Roy, you mentioned the inertial matrix being inverted. It should be inverted, and it appears to be inverted in my code. I don't know if it's not in your code, but hold on, keep that negative in front of the subs. Yeah. Oh, we had negative in front of the subs. Okay. Is equal to minus C Q dot plus minus G of Q, so gravitational, plus tau, right? Well, all this stuff right here, that here is negative EL, oh, it's not everything EL-LHS. That's negative EL-LHS, where Q is equal to 0, right? Sorry, Q double dot is equal to 0. If you set Q double dot as being equal to 0 on the left-hand side, that means this term goes away, leaving this term, and the negative puts it on the other side, right? Okay? And you might all be a step ahead of me here. I'm just trying to lay this out here. And then plus, this is EL-RHS, right? So minus EL-LHS, oh, yeah, I did that right. Okay. And then here you have your inertial matrix. That's your inertial matrix. And everything over here, we're going to call that our bias. Okay. Is there any questions how I've set up the math so far? You all are trying to track what's going on in my code to fix it. I appreciate that. All right? All right? Okay? So that means that if we want to solve for Q double dot, that means that Q double dot is going to be equal to M of Q to the negative 1 times our bias. Right? And that's how we solve for accelerations. Okay? Now going back to our code here, let's talk about this. So the way I look at this, the way I'm interpreting this is that you have your negative EL LHS, and that's what I have here, plus EL RHS, and then I substitute in wherever there were accelerations, I substitute in zeros. So that should be my bias, right? Okay. So I'm looking at your so basically the Coriolis terms here and the gravitational terms, they're all just built into this bias. We didn't have to break them down into subterms. We don't really care what the subterms are for just simulating. We just need to know everything that's in the inertial matrix and everything else that we call the bias term. All right? All right, so we have in arm dynamics, when we're solving for DDQ, why do we not invert M-Func Q matrix? All right, that's a great question, Roy. In my opinion, I think we do, right? We are inverting. Oh, to the... Do you see it? Do you see it, friends? Do you see our issue? Do we see it? Roy, you could have just said the negative, you're missing a negative sign. No, it's my fault. It's my fault, Roy. I can't blame you. Can't blame you. Yes. So, I think we found an issue. We are missing the minus sign. Okay. It is honestly one of the most common things is just to miss a minus sign. Very common error. Yeah. So, let's try that. Let's see if that fixes things, friends. Let's go back to see. I put the minus sign in right there. It should be -1. Invert it, not -1. All right, simulate the arm. We're going to simulate the arm. All right, let's see what's going on. Oh, look at that gorgeous, beautiful double pendulum. See that? Oh. So our dynamics were right. Our dynamics seem to be right. At least they look right, okay? That looks like a double pendulum swinging. Now let's add some rotational inertia. We had turned it off. Let's make it 1 and just see what it looks like. I mean, these are numbers we just picked out of a hat here. Okay, but hey, guess what we did? We debugged. All right, so we regenerated our functions, then we simulate again. And you can see how much it doesn't want to flop around nearly as much, though, right? No, good eye, Roy. That was the issue. Oh, my goodness. People watching the video, people are like, ah, Christian, you don't see it. You didn't see the minus sign. It's right there. Anyway. Okay. There we go. We got that. So this appears to be working, and just we could try some other initial conditions just to make sure that things work. I will say that inertia is pretty big. It doesn't need to be so big. I'm going to make them 0.1, 0.1, regenerate my equations, and let's have a little fun with our initial conditions now that they actually work. So let's start with an angle of pi over 2. This should orient it straight up, and then we'll add a little bit of a kink to the elbow. So 0.1 on our third initial state. A little kink in the elbow. That's about 5 degrees, 6 degrees. All right. And run it. There we go. Fun. That's double pendulum. All right, we have a pendulum. And you can even see the motion of the... Oh, look at this. This is beautifully... This really looks like energy is conserved here. This is just an eyeball. I'm eyeballing it. The fact that the amplitude of the first angle the amplitude seemed to be pretty periodic here, even though you can get chaos here. All right, we did it. It's gorgeous. Okay, let's get back to business. So we have the dynamics. Let's get an operational space controller. Okay. So what do we need to do control? Right now, our torques here, they're zeros, right? We have to have the ability to add torques to this, okay? And so to do that, we're going to go back to our generate arm functions and add in torques that aren't zeros, okay? So let's go back to gen arm functions. Let's scroll all the way down to where we assign our torques. Here we go. EL RHS, the right-hand side. That's the right-hand side of the equation, right, my friends? The right-hand side. We want torques instead of zeros. So what we're going to do is we're going to create some new symbols. We're going to call them tau 1 and tau 2. So these are going to be symbolic torques that we can then substitute in for our dynamics, all right? So right now we're going to have our right-hand side be tau 1 and tau 2. And to be clear, this is going to be, so we're going to add non-conservative forces to the right-hand side. Bingo. Bingo, bango. Glorious. Okay, so they are added in, but then what do you do with them? So where in these functions we're creating, where do the torques show up? Well, do the torques show up in the inertial matrix? No, they do not. Okay? It's only just Q. It shows up in the inertial matrix. But it does show up here in the good old bias terms. Right here, the bias terms. If you can see that, that means that our bias terms here are now dependent upon this new symbolic variable called tau 1 and tau 2. Okay? Which means that whenever we are evaluating our bias, it not only needs to know what Q is and dq is, it also needs to know what tau is. All right, so let's make sure that our bias function now also asks for tau. All right, so how are we going to do that? Well, what I'm going to do is I would say, hey, we're going to have our control inputs u, calling u make it a vector of tau 1 and tau 2. Okay? So these are going to be our control inputs to our system, U. And now all we need to do is say that, hey, our bias terms also needs to know, bias term also needs to know not only Q and dq, it also needs to know U. Like that. Okay? Then we regenerate our dynamics. And we go to simulate our arm, and it yells at us. It's going to yell at us. Why? Because it says it doesn't know what tau is. Which makes sense, because right now our arm dynamics over here, back in our arm dynamics function, we do not pass in our u. We do not pass in our taus. Okay? So let's do that. Okay? Let's pass in some u in our arm dynamics, which means we need to define it somewhere. We could say, hey, we want it to be, just for starters, just make it zeros, right? And see if the code works. See if we get the same thing as we got before. Can you show input line really quick? Your input line, yes. I apologize. I know I'm skipping through this. Back to gen arm functions. Control inputs right here. I would say u is equal to tau 1, tau 2. So it's a vector. Tau 1 and tau 2 on top of each other. That's all we're looking for. Is that what we're looking for, Roy and Logan? Yeah, feel free to stop me for that stuff, okay? You're doing great. You're all the best. All right. Okay. Once you have that, I'm going back to arm dynamics, and I add to my bias function, I added a comma u, because now bias function is now expecting a third input argument. And we have u is equal to 0, 0. Now, because now those will be our two torques, right? Our tau 1 and tau 2 are zeros with a semicolon. All right. I apologize. Like my put this a little bit to the right here. Boom. My face is covering it up ever so slightly. Okay. Now that's saved. Now I should be able to run my simulate arm, and it should work. But now it's applying 0 torque. Yeah, it looks exactly the same, right? Okay. All right, here's what I'm going to do now. I'm going to change my initial conditions so the arm is pointed straight down, because I know exactly what should happen in that configuration. So I'm going to make it, so straight down is minus pi over 2. And then the relative angle, the sort of the bend of the elbow, is going to be 0. We want it straight down. Run that, and the arm should just sit there. No issues, right? Okay, now I'm going to add a torque to it. I'm going to add a torque. So I'll go to my arm dynamics, and I'm going to add a torque to my elbow, right? I'm going to add a torque of 3 Newton meters. That's going to be the second torque, is torque at the elbow, 3 Newton meters. Going to go back to 7. So you change that second one to 3, and I'm going to go run the arm again. Look at this. Yes. Yes, king. Look at that. Beautiful. See, it's flexing the elbow like that? Because what it's doing, exactly, look at that bicep curl. That is exactly what it should be doing. Because what it's doing is it's applying a constant torque, and it sort of overshoots sort of the equilibrium position of the elbow, and then it kind of just keeps coming back down. It would be like if you were applying a constant torque to a pendulum. It would kind of go wah, wah, like that, because it's basically overshoots too high, gravity pulls it down. It's doing exactly right. And you can sort of see the momentum being exchanged between the two links of the pendulum. That's why the bicep curls up, but then the elbow, then the shoulder goes back, right? You see that? Yeah, cool. That's good. All right. That shows that our torque is working, in my opinion. All right, you could do negative. You could show that it goes in the opposite direction, -3 for our torque, okay? And you simulate the arm. You did a -3 for your torque. You'll see it should go in the opposite direction, right? Perfect. Great. And you can check the other torque to make sure it's also doing things. So we'll do -3 for the elbow, but +3 for the shoulder. We'll see what happens. Okay. Just make sure, again, checking things. You can see that shoulder's moving more when you have -3 for your torque in Newton meters. Okay, great. Obviously, we can't be setting this as a constant for the entire simulation. Not going to work. We want a controller to do it. So let's get rid of this line. We no longer need it, okay? Instead, we're going to pass in to our dynamics our control input U. That needs to be an input to our dynamics, right? That's what we need. So I'm going to save that. So I want to be able to pass that in from the from when the dynamics are being called. Okay, going back to simulate arm, and you see I have ODE fun TX arm dynamics TXU. I can add a little x comma u. So now whenever my ODE function is called, it'll bring in my time and my state, and it will pass in some control input vector u, which we need to define in our simulate arm script. Okay? U. Okay, so right now let's just make it our 3, -3. Okay? And this should work. This should work exactly like what we had before, if we did it right. Yes. Look at that. Bingo. That is that really kind of like really energetic bicep curl. Okay? Awesome. Great. Hey, look at this. Look at that over time, that little waveform, right? This is looking good, right? So we now have the ability to add an input torque, right? So, but how do we turn this into a feedback controller? Okay, operational space control is a feedback controller. Right now, this is just a feed-forward torque we're applying. The power of a minus sign, Logan, exactly. Exactly. It all works beautifully. Hey, it shows we know what we're doing. We're setting this up right. You know, we're just little coding errors, right? Okay. Okay, so we have that control torque. But right now, this is a feed-forward control torque. We want it to be feedback. And there's a couple of ways that we could do this. So if you wanted to do a very simple feedback controller, okay? So let's create a simple feedback controller, all right? Where it's just a PD controller, all right? What we can do is we can create you could create that right here where you say U is equal to some function of state, and your state is X. So let's go to our math board. I'm going to go back to the math board for a second, okay? Let's do a simple feedback controller, then we'll get to our operational space controller. Let's just do a PD torque control. Meaning it's just a PD law on the torque. It's very simple, right? All right. So let's just say that our torque 1 is proportional to, some kp1 times theta 1 desired minus theta. So this is a p, and then you have kd1 theta 1 dot desired. So this is theta 1. That's theta 1 up there. Theta 1 minus theta 1 dot, right? This should apply a torque to tau 1 that should attempt to, actually you can't see that very well, I apologize, it's a bit bigger. Okay, here we go. Your forcer's torque, let's just say it's trying to position the shoulder, right? Very simple PD controller. How would you write this? So this would be Kp, this is your proportional error. This is your error, and this is your ddt of your error. Okay, you've seen that before. And we can write that in a couple ways, right? We could say in our code that instead of u, I'm going to have my two input vectors tau, they could be 0 and 0, right? And instead of the first one, I would say, hey, I want this to be this feedback control law. Let's just say you have some Kp of 10 times some desired angle of 0 minus your actual angle, which is your first state x1, plus some Kd term, we'll call it 3. Again, I'm just throwing this all together, times, let's just say you want it to go to 0 velocity, your theta 1 dot desired. Sorry. Okay, let me just walk through this 1 second. That 10 is this Kp. Kp is 10. I'm just throwing this out there. Okay, just trying it. Theta 1 desired, which say my desired angle is 0. That's straight out that way. Okay? And theta 1 is our first state, x1. Kd, I'm saying, is 3. My desired velocity is 0. And my actual velocity, so 0 minus your actual velocity, that's going to be my second state, x2. I could write my controller like that, right? So where it's expecting my control input u, it is instead sending in this. Let's see what happens. And you can see that it's trying to lift up the shoulder to get close to that horizontal angle there, right? So how could we get it closer? We could try upping the gains. I could say instead of 10, I could say let's make it 50. And our KD gain, let's make it 15. I'm just good at thumb in the wind. Kind of, this is vibes-based tuning, as we call it in the controls business. And when you make the gains a little bigger, it's going to, just get a little better at making that shoulder go where we want it to go. And you can still see that the little elbow is just dangling around doing nothing, right? People seeing this? People getting this? So, hey, we made a feedback controller. But it's a little sloppy to put this all in just this one line here. So what we can do is create a new we can create a function. Getting that, Logan? Fantastic. Great to see. We can create a function. We can call it feedback controller. And it is a function of time and state, or just state even if it's a feedback controller, but it's fine. And what it does is it returns our controller, right? I'm going to cut this, cut the controller and put it there. And then I just say, hey, feedback controller T and X. And that should run just fine. Yeah. Okay. All right. So you can just set that feedback. So now it's a function, right? So this function now is a feedback controller. It's a really simple one. So it's a simple feedback controller, but it means that we can create a function that takes in our state, also maybe the current time, and returns our torques, right, that we want to apply. And now it's feedback controller. Nifty. Okay. Now we're going to get to the fun part here. Fun part. It's the operational space control part. All right? Let's hang on to your hats. Because now, this function, which was before a simple feedback controller, this PD torque control, we now want to be an operational space controller. And just as a reminder, okay? Oh, shoot. Okay. So for our operational space control, OSC, we are going to solve some optimization problem. W star is equal to argmin of W, where you want to minimize the difference between some, what we call it, Y. I'm going to remind myself of my notation, excuse me. Yeah, Y. That we have some acceleration in the task space. We're going to call it Y double dot desired minus Y double dot, and it is a norm squared. So this is just a optimization problem where our decision variables are our input torques. Okay. But also, this is a trick I sort of quickly introduced. We're also going to be solving for our Q double dots. Why are these decision variables? Well, it's because we're going to add some constraints. We're going to say that M of Q times Q double dot is equal to our bias, right? These here are our dynamics. So it says, yes, I want to create these accelerations in my task space. And recall, my task is going to be the end effector of my arm. I want my end of my arm to go in a particular direction. Okay? But I'm still subject to all the dynamics of my system. So the accelerations that can happen, well, they're going to be constrained to the dynamics here. Right? And that bias, that's dependent upon, I'm going to write that as dependent upon Q dot, and also our control torques tau, right? And what this does is by writing it like this, this is now a linear equality constraint. This is linear. And this here is going to be a quadratic cost. The quadratic cost, which means that we want this to be this is going to be a quadratic program. Or a QP. And it'll be convex. Be convex. So that means when we go back to this function, this feedback controller, it's not just going to be an equation. It's going to be what, my friends? It's going to be an optimization. So we're going to have to actually run have a function that runs an optimization. All right? Okay? So what we're going to do is we're going to comment out this simple feedback controller. And we're going to create another feedback controller. We'll call it feedback controller equals, and it's now a function handle that takes in time and your state. And right now, just as a placeholder, we're going to say it's 0, 0. Okay? Just a placeholder. Make sure everything still runs okay. Yeah, it seems to run fine. Great. Okay. So now we have to get to the point where we can make this quadratic program. And there's a couple of things we have to be able to figure out to do that. all right? One, we need to have our cost function, which is now dependent upon this y double dot desired and y double dot, okay? So we have to be able to compute y double dot. So what is y double dot? You'll recall, do we define it up above? Let's take a look. It's going to be the end effector, the end of our robotic arm. It shouldn't be hard to define anyway. So our y is dependent upon q, and our task space has two coordinates. It's going to be the horizontal and vertical coordinate of the end of our robotic arm. Just doing your trigonometry, it's going to be L1 times cosine of theta 1 plus L2 times the cosine of theta 1 plus theta 2, all inside the cosine, of course, so there's no confusion. Then you have L1 sine of theta 1 plus L2 sine of theta 1 plus theta 2. Okay? Well, we can define that in our is there a way that we can, so anyway, we're going to need to know what y is. We need to know what y dot is. What's actually dependent upon q and q dot. You could do all the math to take a time derivative of all that, right? And y double dot, right? And that's q dot, q dot, q double dot. You could take your math by hand. You could do those derivatives, or you could not do that. You can let MATLAB do that. And that's what we're going to do. Okay? And we're going to do that inside of our generate functions script. Okay? So if we go back to our math, we go back to our generate functions script, we need to add, my friends, to this, to our kinematics and all this stuff, right? We have to also not just compute the kinematics for our mass centers. We also want to compute our task space. So let me see where I can find that here. I'm going to create our task space right here. After I do my Euler-Lagrange equations, I'm going to define our task space definition. And it's going to be literally the math that we have right here. That our task space, we're going to call it y, is going to be a vector with L1 times cosine of, what we call it, theta 1, plus L2 times the cosine of theta 1 plus theta 2. Then I'm going to do a semicolon. I'm going to put a little ellipsis to put this on the next line. Then I'm going to say L1 times sine of theta 1 plus L2 times sine of theta 1 plus theta 2. And that should define y when I run my genArms function. So I say y. What is y? Hey, y is time dependent. Look at that. Nifty, neato, cool. Right? Not bad, not bad. And what you could then do is say, hey, I want to know what the derivatives, these things we want to compute, I could compute those as y dot and y double dot. And you know what? We can just do that. We can just do that. We could say dy is equal to the derivative of y with respect to time, right? I could run that with derivative of y with respect to time, and then we can check at the end and say, hey, friends, what is dy? And there you go. You have all the chain rule stuff. Look at that. There's your dy. I can't quite see all of it. Let's see. There you go. I get this dy right there. See that? And you can do the same thing with ddy. Oh my goodness, you totally can. Ddy is equal to the derivative of dy with respect to time. And totally do that. Now, that is not actually how, that is one way to compute ddy. Totally valid. You can do it that way. You can see how long d dy gets. That's not that bad. Not as bad as I thought, right? Not too bad. A very typical way, and I talked about this in previous lectures, okay, where we actually use the chain rule to write out d dy, the y double dot, in an interesting way, where y dot, which is equal to the derivative of y with respect to time. By the chain rule, it's the same thing as saying it's the partial y, partial q, partial t, which is the same thing as saying the Jacobian. So basically, where we know that partial q, partial t, that's q dot. Give it a different color. And this right here, that's our Jacobian of y with respect to q. And then you take this derivative again, you get y double dot, you use the product rule. The derivative of the first times the second plus the derivative of the second times the first. This becomes j dot q dot plus j q double dot. That's very typical. So where people will often do is they will get the Jacobian of their task space and then take the time derivative of it and write it like this. The Jacobian, just to be clear, the Jacobian is the same as diff, but for partials, the Jacobian is a derivative with respect of a vector with respect to a vector, and it's particularly a partial derivative. Okay? Okay. The Jacobian gives you the derivative of a vector with respect to a vector. Okay? The diff only works for a scalar with respect to a scalar or a vector with respect to a scalar. Okay? It's a good way to write this out. The diff command will be the partial of a scalar, d scalar, or d vector, d scalar. That will do. The gradient command will do d scalar over d vector. Good question. And the Jacobian will do d of a vector and d vector. Okay. Okay. And the derivative will do the ordinary derivative, but we're only ever taking the ordinary derivative with respect to one variable. So that gives us we use this for all of our ddt's. Great for ddt's, right? You got it. Bingo. All right. Okay. So we have ddy. I just want to show you there's another way to compute ddy using this. That's very common. You'll see this a lot. All right. So now we have ddy. That's awesome, right? Now, ddy is now time dependent, and we have to do the same kind of substitution trick that we did for our left is now, sorry, back to here. Our ddy, you'll see, is now time dependent. Down at the bottom, we had to do all these fancy substitutions, but the good news is we can just do that here, right? So this is when we did our substitutions for removing time independence. I'm going to take these 3 lines of code, okay, and I'm going to copy them, and so I'm going to do the same trick for ddy. All right, and y and blah blah blah. Give me a second here while I think this through. Where there was once ddy, I want to substitute all my accelerations, and then dy, ddy, 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 ddy. Okay? So if I run this, this should now create a DDY that now gets rid of all of the time, a lot of the time-dependent quantities. Let's take a look here. DDY. Bingo. Yeah, so look at my DDY. It doesn't have any time-dependent quantities. The only thing that's kind of annoying is that it still thinks DDY itself is dependent upon time. So what I do is I create something called DDY underscore, where I say it's a new thing, which is not time-dependent. So it's going to be where I grab each of the elements of DDY. And so 1, 1, and then 2, 1. Same trick as we did last time with our Euler-Lagrange, right? Okay. All right, so this gives us our task space accelerations. You'll see that DDY underscore is now not time dependent at all. And this will help us create functions that give us our task space acceleration. Hey, look at that. Boom, right there. All right. We're closer than you think to getting this, all right? Okay, so we now, when we go back to our board, when we look at our quadratic program, we now have our DDY solved in our symbolic toolbox. We will need a function that will give us DDY, which you'll add it for a given configuration. And actually, we could take a look here. Go back to our math. You can see that part of our that it's dependent upon angles. It's also dependent on accelerations. You can see all this stuff. Okay, it's dependent upon those things. So we're going to want to make a MATLAB function that gives us the task space acceleration given q dot, q double dot. Logan has his hand raised. What's up? Let's see. All right, just to be clear, the Jacob. Yeah, I can hear you now. Yeah. Yeah. Yes. Thank you. Good catch. Thank you very much, Logan. So Logan just said, hey, I thought you just pointed out that I should have said 1, 0. Thank you very much. That would have saved us a headache later. Applause for Logan. Thank you. All right. Cool. It's also going to be helpful. Scroll back up. Yeah, what you need. Scroll back up to, so Roy, where do you want to go higher than this? You want to go to where I defined y? Is that what you want? Try to make it as big as possible so you can see what's going on. That's everything for the, almost everything. Cool. All right. What I'm also going to do is I'm going to do the same trick, but I'm going to define dy and y. I want to make functions out of those as well. Okay. I'm going to paste this into the chat so you have it right there, Roy, so I can keep moving forward. There you go. Okay. I'm also going to create y. I'm going to do the same trick here, but I'm going to also substitute in for y and dy. So this is going to be y, our task space. Because what I want to have is a function that takes in q and tells me where I am in my task space. That's going to be handy for later. Same thing with dy. I want to be able to take in q and dq and know where what my velocity is in my task space. Okay? So that ran everything. Let's make sure this all works. So y, good, still time dependent. I still have to do this trick again once more for y and dy. Boom. And that should say y, that should say dy. Make sure I have that right. Yes. Should do it. Cool. Check it. Y underscore. Looks good. dy underscore. Looks good. ddy underscore. I think looks good. Sines and cosines. Great. These are our task space accelerations. Fantastic. So what that means is that we now have non-time dependent versions of y, dy, and ddy. And I'm going to create MATLAB functions that will return those, okay? So let's see. No, we're close. Sorry. Just give me a second. Losing my train of thought. Well, no. Okay. If we have... All right, cool. Now here's what we're going to do. We're going to set up our optimization problem. Since we have a quadratic program, what do we need to know to solve our quadratic program? We're going to help quadprog. Just as a reminder, we have to give it h, which is our Hessian of our cost function, f, which is our gradient of our cost function, a and b, which are our inequality constraints, and any equality constraints that are linear, we have those matrices. So for our quadratic program, it means we should set up our cost. And we did this before back in our quadratic programming testing days, right? Right? Okay. So in our cost, well, our cost right here is right here. Well, sorry, right here, my friends. It's this argument of y double dot desired and y double dot. Okay, so it means we have to start defining our cost function in terms of our decision variables. What are our decision variables? Well, it's these things. It's our torques and our q double dots. Okay. So we're going to define our cost function. We're going to define our decision vector. And we're going to have our constraints. So our decision vector, we'll call it W, has our taus, which we've conveniently stored all in U, right? Okay. And Q double dot, well, which is called DDQ, right? Those are our decision variables. Okay? Then our cost, can we write that in terms of our decision variables? Well, yes, we can. Yes, we can. So we can write our cost. It's going to be some y double dot desired, which we have not defined. So we have to define. So our cost is going to be y ddy desired. That's this term right here. Minus y double dot. Or ddy underscore. Right? Then it takes what we call the norm. Basically, what that is that, so we haven't talked about norms in this class. It's just a little, basic linear algebra, it's the distance formula. So if you have a vector with two elements, one then the other, it's this squared plus this squared, square rooted, and then we're going to square it. As you can see right here, it's a little squared. So if we do the norm of this squared, that should be the cost. Let's take a quick look. It doesn't know what ddy desired is, so it'll yell at us. I'm sorry, I haven't defined it. But that's going to have to be a symbolic. Create a symbolic ddy desired. It's going to be symbolic ddy desired. And it's going to be a 2 by 1 vector. This is going to be our desired task space accelerations. Okay. If we set that up, then we should have a cost function. Let's look at what the cost function is. Bingo. I see an absolute value. I don't like the absolute value. I'm going to write this in a slightly different way, my friends, because the norm function likes to throw in an absolute value, and we're not going to like doing that. Because what we're going to do is, so as a reminder for our quadratic program, this is our cost. I'm going to take the Hessian of that cost, which is our second partial derivative, to give us our h. Take our first partial derivative, give us our gradient, right? So we're going to want to make sure that that Hessian comes out as a bunch of constants. And if you have a weird absolute value function in there, it's not going to work. Okay? So we're going to write this instead as ddy minus ddy desired minus ddy transpose, so dot apostrophe times ddy desired. Why did I do that? Well, just as a little reminder here over in the corner. So if you wanted to know, if you had some vector x was equal to x1, x2, okay? X transpose times x is going to be equal to x1 squared plus x2 squared. Basically, it's going to be x1, x2 times x1, x2. And if you do a matrix multiplication on that, it turns into that, which is the same thing as saying, oh, this squared plus this squared, square rooted, all squared, right? So that's that. So this x transpose x is exactly what I'm doing here. Here's that difference, transpose that. That's your cost function. So you run that, and we look at our cost. Boom. Question. So do we need the square root? We don't, because what do we do once we do the square root? Look at our cost function. Our cost function will then be squared. We're squaring it. Okay? Great question, Logan. Could you paste the subs portion into the chat for y? Sure, you got it. 1 second here. Here's all the subs for y into the chat. Boom. Done. Okay. We have our cost. That means that we can take the Hessian of that cost with respect to our decision variables. So we did our Hessian of our cost in the command window. You can see it'll give us, boom, Hessian. Bingo. So here if we say the Hessian, call it capital H, is equal to the Hessian of our cost with respect to W. Awesome. Okay. And we had our gradient. We're not using f right now, are we? We are not. Fantastic. What about lowercase c? We're not using c. We're not using c either. Call c our gradient. That's the gradient of our cost with respect to w. But recall that once we take the gradient of our cost, c, we also have to then set all of our decision variables to 0. Because right now, if you look at all your decision variables here, you'll see decision variables in your gradient here. Blah, 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 blah. Where's our decision variables? Here. That's a decision variable. We don't want that there. We don't want that there. So we then have to say c is equal to the substitution of c, where you once had decision variables w, you now have zeros of the size of w. Then you have your gradient. So you got c. So now you look at c, look at h. You notice that h is not, if you look through your h, you should only see things like thetas, d thetas, but not decision variables. Because what are our decision variables? They are taus and q double dots. Okay? And the same thing with c. Great. We have our Hessian and we have our gradient. Okay? Awesome. Now we just need our constraints, right? Right now we only have equality constraints. What are our equality constraints? It's that m times q double dot is equal to your biases right there, right? Okay? So our equality constraints here, I'm going to rewrite this. Sorry, you can't see this at all. I apologize. I'm better than this. So we are at our decision vector right there. What are our constraints? This. Those are our equality constraints. So I'm going to rewrite this in big letters here. Let's write this down below. So our constraint, or equality constraints, are that m of q times q double dot is equal to our bias of q, q dot, and our taus, right? Well, my friends, if q double dot, that's the worst q double dot I've written. Q double dot is the decision variable, okay? And these things are not decision variables, and Q is not a decision variable. That means this is going to start to look a lot like the form AW is equal to B, right? These are linear constraints, okay? So what I'm going to do here is I'm going to create some equality constraints that say that AEQ times W minus BEQ are equal to 0. And then I'm going to solve for, this AEQ with a Jacobian and a BEQ. The thing is that, because unfortunately our W is, actually tau is a decision variable. This is why we have to do this. Okay. All right. Give me a second here. I apologize, friends. All right. This is the decision variable, taus. And q double dot are decision variables. But they should be linear, this constraint. So let's set up this constraint and then put it into this linear form here, this AEQ times W equals BEQ. So if we go back to our code, we have our equality constraints, so we have our dynamics. So we're going to say that m of q times q double dot minus your bias is equal to 0, right? So m of q times, sorry, it should be q underscore, times ddq underscore, these are the non-time varying versions, minus your bias must equal 0, right? Call that our equality constraint, EQ con, right? Our AEQ is going to be our Jacobian of EQ con with respect to our decision variables, W. Okay? And BEQ is everything not multiplied by our decision variables put on the other side. So it's going to be minus the substitution of EQ con. And where there were once decision variables, there are now none. So we say zeros, W, size of 0. Okay, didn't like one thing. What did it screw up? What did I screw up here? All right. All right, subs refs. It should be 128. It didn't like this. What did I screw up? M? Oh, M is already a function of Q. Get rid of that. Sorry, get rid of that. You don't need that M of Q. That's what the issue is. It already knows, symbolic toolbox knows that there are Q's inside of M. Okay. All right. So what did it not like? Ha. Give me a second, friends. Did I fix that here? It doesn't like 130. Doesn't like the way I'm doing the substitution. I'm not sure why. Because I'm just going to substitute wherever there are W's, I want zeros, right? Why not do it like this? Subs, EQ con, zeros, size. Isn't that what I did? Oh, W. Oh, I'm sorry. I screwed up. Thank you. You're absolutely right. I don't know why this is a typo. Yeah, thanks, Roy. Yeah. You both picked it up, but Sam, I don't know why I put that there. Delusion. Here we go. That works out fine. AEQ. You're all on top of it. Look at that AEQ. Bingo. I don't see any decision variables in there. Thetas are known at the time. They are measured. BEQ. Thetas, D thetas. Are there any taus in here? I'm looking for taus. The only thing I'm not seeing are taus yet. Can you all see? I'm expecting somewhere in the dynamics for the taus. Oh, no, the taus are decision variables. Of course, I'm so silly. So silly. I also, friends, I have made a grievous error. Okay? It's easily fixed. All right? And this is something I should not blast over. And by the way, thank you all for coming today. If you have to jet, I understand. I will put all this stuff online, of course. Okay? I'm realizing I made an error in the dynamics that's hard to check, hard to get. Okay. All right. Look at this tau. Okay. When we're adding to the right-hand side right here, this is a dynamics catch. So let's go back to our dynamics. It's a very simple physics thing I forgot. That tau 1, when it's acting on this elbow, that means that tau is acting on our first degree of freedom, which is theta 1. That's totally true. And we have tau 2, it's acting positively on theta 2. That's true. But because that motor is also going to be attached to the other linkage, you have an equal and opposite torque back on theta 1. So it's really easily solved. So all it means you have to do is you have to go into your code, go up to where we were covering the, we're adding the ELRHS on the right-hand side. In the first row, you have tau 1 minus tau 2. Tau 1 minus tau 2. Okay? That fixes that. Otherwise, that tau is coming in from outside of the robot arm because there's no equal and opposite torque on the other part of the robot arm. Okay? We'd call that like a hand of God torque. Right? And believe it or not, friends, we actually have the quadratic program almost ready to solve. Okay? All right. So just remember, just add that there, the minus tau 2. So if you don't have that torque also acting back on the shoulder, on its upper arm joint, I should say, then it's like a hand of God is coming from outside of the arm to apply a torque. And that's not how motors work. You have equal and opposite torques on the things that are attached to. Okay, so we have AEQ and BEQ. So now we need to just create MATLAB functions that export these. So we're going to call it the Hessian, H, the file, we're going to call it the hfunc, and it's going to be dependent upon which variables? It's going to be dependent upon Q. It should just actually be Q, if I'm not mistaken. I think. We'll find out soon enough. It'll yell at us. All right. Then we also need, I'm going to copy this line. We want our gradient C func. It's going to be dependent upon Q and DQ. We also need, for our optimization, we need our constraints. So we have our AEQ is AEQ func. And that's going to be dependent, I believe, on just Q. You can add DQ and there's no harm, no foul. And then you have BEQ. Let's take a look at AEQ. Yeah, boom, only dependent upon angles. If you threw in DQ, no harm, no foul. It's not a big deal, but it doesn't show up in there. It shows up in BEQ. Here you have your velocities. Okay, so BEQ, BEQ func, DQ, Q, and DQ underscore. Okay. All right. So if I run this, this will now create a function that gives me my Hessian, my gradient, my equality constraints for a given Q and DQ. I am missing one thing. I'm missing one thing. DDY's desired. Okay? And that shows up, I'm pretty sure, where? Okay. I'm going to show it up, have it show up. It only shows up here in the gradient when I'm doing my gradient C func. So I need to define DDY desired. Excuse me a second. Yeah, DDY desired. There it is. So I'm going to say Q, DQ, DDY desired. Okay. Run that. DDY desired. Okay. Looks like it worked out fine. And now off to my left over here, you see it's got AEQ, BEQ, my Hessian, my gradient, everything I need to solve my quadratic program, right? Right? Right. So let's go over to our simulate arm function. I'm going to use operational space control to control my task space acceleration to be some desired task space acceleration. I'm going to make it 0. The question from Roy is, why wouldn't the Hessian be dependent upon its torques if torques are in the input vector? Well, that's a great question, Roy. I'm glad you're paying attention. I mean that in the best way. It's a great question. Let's look at our cost. Because the Hessian is of the cost, right? Where's our cost function? It is the task space, right? The task space is just saying, hey, where is the end effector? It doesn't say anything about the position, right? Isn't that neat? Isn't that neat? All right, back to the code. All right. Okay. So we have this feedback controller. I'm going to need to solve a quadratic program inside of it. So I don't want to get too fancy here. So we got to make a new file real quick. I'm going to call it operational space controller, or OSC. New file, function. What does it return? It returns use. What does it take in? It takes in. So it's going to call it operational space controller. It takes in the current state. It takes in the current state. Maybe time as well. Time, state. You don't really need time. And our desired DDY desired. Okay. What does it do? Okay, save it. Operational space controller. Okay. First thing we need is the Hessian. So we say it's hfunc, and it was dependent upon Q. So we're going to need to know what Q is. So let's say that Q is going to be x1 and x3, right? Those are our two angles, right? These are our generalized coordinates. All right. Then we're going to copy, control, shift, paste. DQ, we're going to need to know that. That's going to be our second and fourth states, right? Okay. Now, H is equal to hfunc right there. C was equal to cfunc, which is dependent upon Q, DQ, and DDY desired. Now, Roy, if you wanted to, you can make all these things dependent upon DDY desired. They just don't show up in there. It's no big deal. Okay. This sort of lets you know where these terms actually show up in your Hessian and gradient. I'm sort of just showing you. Okay. So this is our quadratic cost. quadratic cost. Okay? Now we have our equality constraints. AEQ is equal to AEQ func, and that takes in just Q, if I recall. And BEQ is equal to BEQ func, and if we recall, that takes in Q and DQ. Now we need to solve a quadratic program. Our optimal decision vector, W star, is equal to quad prog. We have to give it our Hessian, H. Our gradient, C. Our A matrix, this is for inequality constraints. We currently don't have any. So we just make them open, close parentheses. But we do have equality constraints, AEQ and BEQ. All right? If we wanted to add lower and upper bounds, we absolutely can. And maybe we will. So that's W star. The torques we want to apply, U, are the first two elements here of W. So it's going to be W star, 1 and 2. And we're done. These are the torques. These are the optimized torques. Okay? All right. So now, my friends, we have an operational space controller in this code, right? This runs the quadratic program. Let's go put it in the simulation and see what happens, my friends. Let's change this feedback controller. Instead of being T and X, it's going to be operational space controller. Takes in T, X, and DDY desired. And let's define DDY desired. Just make it 0 and 0. Okay? 0 and 0. I want it to not accelerate. Okay? And then I ran my code, I didn't even tell you. And then nothing happens. Okay, I guess that makes sense. See, look, my pendulum is pointing down. Let me get this out of your way. I apologize. Nothing happens. All right. Not too bad, right? But what happens if I change my initial condition here? Let's change my initial condition. Instead of minus pi over 2, let's change it to 0. I run it. Hey, nothing's happening. My friends, nothing's happening. Why is nothing happening? It's not moving. Our operational space controller is working, my friends. Let me change my initial condition again. Let me change this to positive pi over 2 right there. Run it again. Run my code. Nothing's happening. I am commanding my controller to have 0 acceleration at the end effector. So it is actually computing the torques necessary to maintain that position, or specifically to have 0 acceleration, right? Isn't that neat? Isn't that neat? So let's do one even a little bit better, okay? I said 0 acceleration, not no motion, right? There's a difference. So if I give it a little initial motion, it should continue to accelerate. It should continue to move, but not accelerate. Isn't this neat? Can we get a plot of torque over time? Yes, that's a little trickier than you might think, Logan. But yes, we can get that. All right, it might take a little longer. All right, but let's do something else. So let's give myself an initial velocity of the elbow. I'm going to make it a little bit downward. I'm going to make it like minus 0.01, which means that it's going to start in this position like this, and it's going to start drifting downward, hopefully, if we're doing this right. Let's see if this works right, okay? Until things go crazy, but you'll see. You'll see. Hopefully we'll see. You see it slowly drifting? Maybe it's a little too slow. You see it a little too slow. I'm going to make this 0.05. See what happens? Oh my goodness, it's actually working. Okay, I'm going to change this to minus 0.01. Okay, eventually it's going to create an issue. It's okay. Watch. What it's doing is it's trying to maintain the velocity of the end effector. It's initially starting motion like this, and the operational space controller is making sure that that doesn't accelerate. There's an initial motion, and it maintains that. But then it hits this elbow point right here, right? And all of a sudden, it just snaps in place. There's nothing that the controller can do to push it any further, right? Once it hits like the limits of its motion. Do you see that? Is this making sense to people? I'm just trying to come up. I'm adding a little bit of initial velocity. See what happens. Let me try make that 0. Maybe make this 0.1. Look at this. Oh, perfect. That's exactly what I want. It's moving horizontally at a constant velocity. It's going to keep trying to maintain that. Oh, it's so cool. Oh, it's so cool. All right, so I'm going to change this to 0.2. The operational space controller is going to maintain the acceleration. It's going to keep trying to move to the left. To the left. See that? Now, eventually, we won't be able to go any further. Oh, that's gorgeous. Is it making sense to anybody? Right now, it's not a control. It's not really. It's not tracking a position yet, but we can change that. All right, we can change that. So I'm going to change this to 0.4, and so I just want to show you that it's just going to try to keep maintaining 0 acceleration because I told it I want 0 acceleration. I told it right here. Look at that. Eventually, it'll freak out. It can't do any better. Oh, look at that. Oh. This is really cool. I'm telling you, this is neat stuff. So it's controlling velocity to be constant since acceleration is 0. Exactly, Roy. Exactly. It's only looking at the task space acceleration, which I told it. 0 task space acceleration. That part works. That's amazing. Now, my friends, let's tell it to have something other than a 0 task space acceleration. Yes. So now we can try. So the question is, how do we tell it to go to a particular position? That's what Roy is asking, and that is the question. Well, we did talk about this last lecture. Let me show you. Where is it? Where is it? Here. We can define a control law where our y double dot desired is dependent upon some y desired and some y dot desired. Okay? And we do a little PD control law, but on the accelerations. Okay? And this is why when we did our gen arms function, and when I told you we're almost done, I'm actually, I think it was only partly lying, right? This is working. This stuff is working here. So when you look at your generate functions, we went through the trouble of creating y and dy here, even though we haven't used them yet. And why is that? Well, I want to create a function that I can send in q and dq, and it tells me my current y and dy, so I can use it for this control law where I have y and dy. So let's make just a couple of other MATLAB functions at the very end here. We're going to say MATLAB function. We'll call it where you have y underscore is going to be where the file is going to be called yfunc with the variables. And it only takes in what? It's only dependent upon q. And then I'm going to copy, Control-Shift-C this. And I want my dy underscore, I'm going to call it dyfunc, and it's dependent upon q underscore and dq underscore. Okay, I'm just going to paste that into the chat. Now I'm going to try to tell it to go to a specific position. All right. And how are we going to do that? We're going to go back into our simulate arm. And where we once had this dy controller is equal to 0, 0, I'm going to comment that out. My desired acceleration, I want to be a function of my current state. So it's going to be some, depending upon t and x, but also some y desired and some dy desired. Okay? And it's going to be a controller, just like I wrote right here. Going to make it some constant kp times y desired minus y func of, oh my goodness, we need to know q and q dot, right? This is going to be a little annoying to write, but I am committed to finishing this as long as you're committed to finishing this, my friends. All right. It's going to be x, 1, and 3 are our q's, right? That's q's. Plus, I'm going to put a little dot, dot, dot here. It's a little messy because basically it's just saying, hey, our first and third state, those are our q's, right? Those are our positions. And then I'm going to say plus kd. Again, we have not defined these gains. We'll define them in a second. Times dy desired minus dy func, and we need to give it our q's, which are x with 1 and 3, and I'll copy this into the chat as well to make sure we don't miss anything. And our velocities 2 and 4, right? Did I get that right? That should be dy desired, right? And I'll paste that into the chat just so you have it a little nicer. Thank you for your patience. Let's see if this works. Let's see if it works. All right. And so that means that we have to create a, so dy des is now a function of time, state, and let's give it our position. Let's make it 0.5. I'm going to put this on the next line so you can see it. 0.5, semicolon 0.5. And our velocity, let's make our velocity desired is 0. 0, 0. I'm going to put this all in the chat, see if it works. Wouldn't dy desired need only, no, the task space of, it's a great question, Roy. To know the velocity of the end effector, you not only need to know the angular velocity of the arm, you also have to know the position of the arm, right? The configuration of the elbow will tell you how fast this is moving as well, right? You also need to know Q. What did I screw up here? KP. Oh, we didn't define our KP. KP, 10. KD, 1. Did I screw something up? Feedback controller, TX, Y func. Oh, did I not run my, I didn't run my generate functions. You have to run generate functions. I'm going to run that real quick while I pull up that code again. So, yeah, my functions were not generated yet. Hopefully I did that right. Seems like we did, maybe. Oh. Ooh, look at that. All right, it actually seems to try to track to a position of 0.5. Pretty beautiful, right? I would say it's a little bit too, the oscillations are a little too big. So we can make KD a little larger. We'll make it 3. And I want to go to, yeah, we'll go to 0.5. Here we go. KD is 3. Awesome. And you can mess around with these gains, but now the thing is these gains are being applied to the acceleration of the acceleration of the system, the acceleration of the task space, which means if I were to change something about my arm, if I were to change the mass of my arm, this all should still work. I'll show you. I'll show you. So if I go to my generate arm functions and I changed my mass of my second link to 3, I'm going to change it right back once I'm done with this, but I'm going to regenerate my functions. Okay. But now, like my forearm is 3 times heavier than my whichever, I don't know which arm is which. But anyway, is 3 times heavier. And I run simulate arm, it should behave exactly the same. Exactly the same. Because it's aware of the dynamics. It's all built in. Isn't that great? It's all built in there. It's really cool. It's really cool. What can I? There we have an operational space control. Let's make it do a dance. I agree. I think we should make it do a dance. Let's make it do something fun. The way that we would change this is we have to change, instead of having it track, I'm gonna copy this, Control-Shift-C. I'm gonna comment it out, and instead of going to a constant position, I'm gonna have it draw a circle. Okay, how would I do that? Well, I'm glad you asked. I'm going to say 0.5 times cosine of t. We have access to time, right? 0.5 times sine of t. And instead of 0 velocity, we take the derivative of these, right? This would be minus 0.5 times sine of t. And this is going to be 0.5 times cosine of t. Right? I run that. How awesome are we? How awesome are we? Isn't that cool? It took 2 lectures and also a bunch of time at the end, I won't lie. It's drawing a circle. It's drawing a circle. Let's change the radius of that circle. Right now it's 1, it's 0.5, let's change it to 1, 1, 1, 1. And you could use the symbolic toolbox if you wanted to automatically take this derivative of for your velocity, right? There you go. There you go. Drawing a circle. This is really cool. So if you wanted to change the angular frequency, we can change the angular frequency, whatever. One thing I want to do is if I change the angular frequency of the circle in one direction versus another, if I double it, it'll give me a figure 8. It'll give me a figure 8. I'll show you what I mean. So I'm going to create a figure 8 by making this 2 times t, and then the derivative should be 2 times t, and then 2, if you take the derivative. This is a figure 8. See what happens. See if it works. It might hit a singularity. We'll see how it works, but it's drawing a figure 8. Now, where it gets tricky is that when the elbow is either straight or folded up, that matrix M, the mass matrix, becomes singular, called a singularity, meaning it's basically like dividing by 0, so it can create some real snappy motions. And the reason it's doing that is basically because it feels like it needs to have infinite torque to get the acceleration it needs. So we can add torque limits. Watch. Let's add some torque limits, so that way it doesn't be quite so snappy. So let's go to the operational space controller. We can add lower bounds and upper bounds to the operational space controller. Lower bounds and upper bounds. Lower bounds. Well, our lower bounds on torques, which are our first, where's our torques? Is it our first 2 are torques, right? Let's create a tau limit. Let's just say it's 10. So our lower bound is going to be minus tau lim for the 2 torques, tau lim, and then the second 2. Where is everything? Decision variables. Where are they? Here they are. Shoot. My first 2 are torques. My second 2 are accelerations. I don't care what my acceleration limits are. Those are just whatever they are. So minus inf. And then my upper bounds, they're just going to be the inverse of the lower bounds, the minus of the lower bounds. And now we have torque limits. The operational space controller has torque limits, and it's aware of it. Okay. All right. Now we're going to. I'll put this in the chat real quick so you have it right when we're solving the quadratic program. Okay. Now you have that. Now I'm going to run that. Run it again. Let's see that figure 8, please. Oh, I made the torque limits too low. It's struggling. It's struggling. It's struggling. Can we see plot the end effector to see the path? Yes, we can do that. Yes, we can do that. As long as you guys are good to do that, I'm good to do that. You're all doing way over time here. I'm here for the enjoyment and fun. We can have it plot the path. I was limited too much in torque. 10 isn't enough to hold up that arm. It's too heavy. In fact, you'll remember that we made the mass of the link 3 instead of 1. I'm going to change it back to 1. Let's plot the path when we're done here, okay? Okay, I changed it back to 1, the mass, and I regenerated my equations, and I run my simulation. Still not good enough. It's struggling to do it. So let's make let's make the torque limit bigger. Let's make it like 30. 30 torque limit. Yep. And so let's now plot the path so you can see what's happening, okay? So in fact, we can make this, let's try to make this code a little cleaner so we can define the path, all right? Let's draw the path of the arm, draw the path of the arm, okay? So we got to do this inside of the animation. So we have the animation, we want to plot the path. So what we can do is for every iteration of the animation, we can just add an additional element to a vector that's going to just plot the path every time. So right now we have x points, z points. It's already being computed to draw our arm. So what we can do is we can create something called an x path, which is an empty vector that's going to get longer every time, and the z path is the same thing. So it's going to be an empty vector that gets longer every time, the x and z coordinates of our path. So we're going to say that x path is going to be equal to x path semicolon. So we're going to add onto it the end effector point here that we're already drawing, which happens to be right here. It's the last element of x points, right? And we can do the same thing by Control-Shift-C copying. It's going to be z points, okay? And that's going to be z path. All right, so we're going to then want to maybe do a little bit of a hold on. Where we can clear, yeah. So we already have a hold on. Sorry, we already have a hold on. So this plots the arm. But this is going to, but before that, we're going to plot the path. So the arm is plotted on top of the path. So we're going to plot the path. So we're going to say plot x path, z path, and let's make it a line. But the color of it's going to be a nice light gray. So the color, we say color, and I'm going to give a color code of 111 is completely white. If I multiply it all by 0.5, that'll scale it back to like a 50% gray. Okay, I'll set the color right there. And this should create a path. Let me see if I can get this down here so you can see it all while the path keeps going. There you go. You can see the path going. Now the challenge is that the path goes right through the middle of the arm. So what we can do is we can offset that just a little bit. If we move it like a little bit to like the left, it won't go right past the base and hit that singularity. So we can move that around. Okay. Why I have two things going is interesting there. Oh, x points end, the last element, right? Right. That's what we're missing. End. We need the last of the points, right? That's why. We're now trying to draw like the elbow and everything else, which is actually not the end of the world, but you know. What do we want to change? Let's change the position of the desired trajectory just a little bit up. Let's make it a little higher. So let's add 0.2 in the feedback controller. This will push the figure 8 up, so that way it's not overlapping with the base of the arm there. All right, let's run that. And now we should have a nice little figure 8. Still a little bit too close for comfort, it seems, to the center of the. So let's go 0.5. There we go. Now we're talking. 0.5. I had a little 0.5 right there. So people see what I'm doing? This is cool, right? This is why I teach this class. Anyway, so I think that's a great place to leave it for today. We have a fully functioning operational space controller. We can even apply torque limits to our operational space control, right? We can change those torque limits. And it does the best we can, right? This is really neat. This is really cool. So thank you for doing this with me. I know we went well over time. But the good thing is you have this on YouTube forever. All right, you can mess around with the pattern that you want to draw. You can change the inertial parameters of the double pendulum, and it still works. You can change the lengths, and it still works. The only thing you got to do, you want to make sure that when you animate it, that you change the length too. So like if we were to change this to like 1.5 for the length, right? We can change that to 1.5 there, and then we go to simulate the arm wherever we define L1 right here. We change it there as well, right? 1.5, and we run that, and that should run the same thing. Hey, look. It's a little tricky because it kind of goes very close to its singularity again, but you can see, look, hey, it might be better if I had made that 0.5. 0.5 as the length one. I'm just messing around now because we did all the hard work already. So the gen functions, we made it length 1 is 0.5 in both the animation and the arm. If you wanted to be fancy, you could have it so you change it only in one place, right? Okay, runs the regeneration. Let's simulate the arm. One other thing I want to point out is that it's solving a quadratic program at every step. What is? Oh, it's so tiny you can't even reach the places it's supposed to go, but it's doing its best. It's doing its best. It's trying. It's trying. It's doing its best with the Optimus controller. Oh yeah. So let's follow up with some things. Let me change this back to 1 and 1. The thing I was going to say is that it is solving a quadratic program every single time step that ODE 45 is checking, which can be slow. It's good enough on modern computers, but what you can also do is have it solve the quadratic program once. Find the torque, simulate it for like a little bit of time, and then resolve the quadratic program again and restart the simulation. It's similar to what we did with model predictive control. We could do that exact same thing, but it didn't matter this time. Number 2, people said they would love to mention why applying the torque profile would be tricky. I'm glad you asked. It's because the simulation. Why is it tricky to plot U over time? Okay, it's because the simulation, which you're running for ODE 45, what does it return? It returns time, and it returns the states, none of which are your control inputs. Your control inputs are not states, right? Your control inputs are dependent upon states. All right. So what you could do is after you simulate, you do a loop where you say, hey, at every one of these states, what is the control input? And then store it in a new vector. But it's just not stored in the simulation. That's why it's tricky. It's actually one of the things that's a little bit trickier. But hey, I have no life. I have things I should be doing, but I could be here with you. So let's try to store the control inputs from the simulation. We have to recalculate and calculate them. Okay, so which point, what do we need to know? We have a feedback controller, right, which is dependent upon ddy des, and is dependent upon tx. So what we can say is, hey, feedback control. Yeah, here's what we'll do. Recalculate them. First, we're going to pre-allocate a vector of control inputs. We'll say that each column is a different input. Each row is a time point. So that way to line up with xsim. So we're going to say usim is going to be, we'll just pre-allocate it with zeros, and it's going to have the same number of rows as we have time points, so it's number of elements in tsim, and we want to have, and we have 2 columns, right? Okay. And we have to do something I don't do very often, friends. Write a for loop. I don't. You'll notice I try to avoid for loops at all costs. We have like 2 for loops and 1 for loop in this entire thing, and it's just for the animation, right? All right. So 1 colon number of elements in time sim, right? tsim. Okay. For each of those elements, we say that usim, the current row, so it's going to be the current row, iter, and all the columns, is going to be equal to our feedback controller, which returns our control input u. So feedback controller. What does feedback controller take in? It takes in current time and current state. Oh, isn't that convenient? So whatever tsim iter is, and whatever xsim, again, it's the current state, so it's going to be the current row, all the columns. But so it's going to be all the columns of the current row. So we want it to turn it into a column vector, so let's do a transpose, right? And so what's going to come out of this is going to be a column with our 2 torques, 1, 2. But we want to store it in a row, so what do we have to do to it again? We've got to transpose it again. Boom. Okay? And don't forget the semicolon. All right. And that should be usim. Let's see if that doesn't throw an error when I run it. Okay, it didn't throw an error. Not sure why it's going crazy now. Do we ever get it to work right? I don't like, there's something not working right about this the way it was before. Let's screw something up. Feedback. Let me go to the mass. Oh, you know what? Maybe I didn't regenerate. That's the problem. I probably didn't regenerate my functions. That's probably what happened. Thank you. Let's try that. See if it now works. Simulate ARM. Yeah, so if it doesn't regenerate, then it is working with the wrong dynamics, right? There we go. That's what you all see, right? Great. Cool. Nifty, neato, awesome, cool. Now we are storing U's. So now let's actually plot U's over time. So let's create another subplot. So we had 2, 1, 1 subplot. Let's make 3s. 3s. Subplot. 3, 1, 1, 3, 1, 2, now 3, 1, 3. These are going to be both of our torques, right? X label, time. I'll just copy paste time. And that's going to be torques. Motor torques. Newton meters. Okay, but what do you have to actually plot? We're going to plot. We're going to do a hold on because we're going to plot 2 things. We're going to plot. We're going to plot our tsim, but then also our usim for our first torque. So that's going to be our entire first column. We'll make it a red line, And then we'll make another one that's a blue line with the other torque, with the second torque. And we could hold off even though it won't matter. Okay. If I run that, let's see if that works okay. Hey, look at that. It's like we know what we're doing. Let me get this out of your way here. Let's run this here. Sorry. I blew it all away. There you go. Plots of torques. Hey, where's it limited to? Like 25 or something? 30? 30. We limited it to 30. Can y'all see that? Anyone need to see anything? Great. Oh. That. I just added a third subplot with my torques. Exactly. That's all I did. That's all I did. Operational space control from scratch, my friends. Cool. That's it. We're only an hour over time, so thank you all very much for coming. I hope you all had a good time. I hope people watch this later. Yeah, thank you very much. And so we got some cool stuff going on. We'll have one last coding lecture on Thursday. What will we cover then? Honestly, I'm open to suggestions. We can code or whatever we want to code. Yep. I mean, so the question is, can we have operational space control track a moving target? I mean, literally right now we have operational space control tracking a moving target, right? Yeah. 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 So right now, if you wanted to change how the target moves, what did we do? It wasn't the most clean way we wrote how the target moves for operational space control. This here is our Y desired, right? So we wrote it as this. And our dy desired said, hey, time derivative of that. And we are just really good at derivatives in our heads. So that's what it is, right? So cool. All right, I will release you all. I look forward to seeing you all on Thursday for those who want to come. Take care.